Quantum Supremacy: How the Quantum Computer Revolution Will Change Everything by Michio Kaku.
Right.
You're listening to COSMORA HQ, where we explore the science, technology, and transformative ideas shaping humanity's future. What important problems could quantum computers solve more effectively than classical computers? And how much of the promised quantum revolution represents demonstrated capability, credible forecasting, technical aspiration, or technological hype?
That is the big question.
Yeah, I mean, imagine a machine that has to be kept colder than the vacuum of deep space just to run a calculation that would take our best current supercomputers, like 10,000 years to finish.
It sounds like pure sci-fi.
Exactly. So today we are diving deep into Michio Kaku's visions, and we're going to try and separate the science fiction of quantum computing from the actual engineering reality.
Right, and we really have a monumental task ahead of us today. We're going to examine why classical computers are physically hitting a brick wall right now.
Which they are.
Yes. And how quantum mechanics offers a fundamentally different architecture for processing that information. But more importantly, I think we are going to apply a pretty ruthless evidence ladder to this entire field.
Okay, an evidence ladder?
Yeah, we'll climb from just the pure mathematical theory up through the harsh reality of hardware engineering as of August 2026, and we'll carefully delineate what has actually been built in a lab versus what exists only on a corporate slide deck.
I love that, a reality check. So I want to start by figuring out why we even need to reinvent the computer in the first place. Because the silicon chips we have now, they power everything from smartphones to global supercomputers, and they seem to be doing just fine.
They do seem fine on the surface, sure.
Right. For decades, the rule was just make the transistors smaller and pack more of them onto the chip. Why can't we just keep shrinking them forever?
Well, because you eventually hit the fundamental fabric of reality, which is atoms.
Oh, right.
Yeah, a transistor is essentially a tiny gate that stops or allows the flow of electrons, and it represents your ones and zeros.
The basic classical bit.
Exactly. And when those gates were microscopic, they worked perfectly. But as manufacturing has pushed them down to the size of literally a few atoms across here, run into quantum tunneling.
Quantum tunneling.
Yeah, so the barrier is so thin that the electron simply pops over to the other side, even when the gate is officially closed.
Wait, so it just teleports through the closed door?
Basically, yes.
Yeah.
And that means you get massive current leakage, which generates incredible heat.
Yeah.
So the physics of shrinking are actively turning against us right now.
Wow, okay. But the classical tech industry isn't just, throwing up its hands and surrendering, are they?
Oh, far from it. Classical computing is what we call a moving baseline.
Okay.
We are getting incredibly clever with multi-core processors, distributed cloud clusters, and highly specialized accelerators like GPUs. We also have these massive algorithmic improvements like tensor networks.
Okay, let's pause right there. What is a tensor network? Because that sounds like some very dense academic jargon.
Fair point. Yeah. Think of a tensor network as a highly optimized mathematical structure. It's designed to handle complex relationships between variables without needing to calculate every single interaction individually.
So it's a shortcut.
Exactly. It's a shortcut for classical computers to simulate very complicated systems, including quantum systems, much more efficiently than we thought possible even 5 years ago.
Oh, wow.
So when someone claims a quantum computer will eventually be faster, they have to beat the absolute best classical supercomputers, which are armed with these new shortcuts and continually evolving hardware.
Right, so quantum computers have to hit a very fast-moving target.
Exactly.
Okay, let's unpack this. Let's look at how a quantum computer even attempts to hit that target, and it all centers on the qubit.
Right, the quantum bit.
Yeah, and I hear this analogy constantly. I want you to tell me if I'm crazy here. People say a classical bit is a coin sitting on a table. Heads is 1, tails is 0.
Right, that's the standard analogy.
And then they say a qubit is a coin spinning the air, basically magically being both heads and tails at the exact same time until it lands.
Yeah, that analogy is entirely misleading, and we really need to dismantle it immediately.
I mean, really?
Yes, a qubit is not simply two readable classical bits packed into one. That is a huge misconception. You cannot pause a qubit and read a simultaneous 0 and 1.
Then what actually is the state of a qubit before we look at it? Like, what is it doing?
Its state is defined by complex mathematical amplitudes.
Amplitudes.
Yes. These amplitudes dictate the probabilities of what you will get when you finally measure the system, along with the relative phase between the states. It is not a magical box containing multiple readable answers.
Okay.
The second you measure a qubit, that delicate probability wave collapses. You force it to choose, and you only get one allowed classical outcome, which is a 0 or a 1.
Oh, I see. Which actually shatters another massive myth I see on tech blogs all the time.
Which one is that?
The idea that quantum computers are infinitely fast because they calculate every possible answer simultaneously and then just kind of pluck the correct one out of the pile.
Yes, I hear that constantly too, and it completely misunderstands the physics. Quantum computers do not reveal every possible answer simultaneously.
They don't.
No, they don't. They use a property called superposition to access those complex amplitudes across many alternatives.
Yes.
But as we just established, almost all of that rich information is permanently lost the moment you take a measurement.
So it all just vanishes.
Exactly. If you load a problem into a quantum computer and put it in a massive superposition and just measure it,
Yeah.
you don't get the right answer. You just get a completely random string of useless noise.
So if it's not guessing everything at once, how on earth is it computing anything?
Well, that is where it gets really elegant.
This brings up my absolute favorite concept in the field, which is interference.
Yeah.
Tell me if this works. Imagine a giant wave pool, right? If you just splash the water randomly, it's chaotic noise. But if you carefully time two wave generators at opposite ends, the crest of one wave can meet the trough of another.
Right. Destructive interference.
Exactly. They cancel each other out. But where two crests meet, the wave doubles in height and you get amplification.
The wave pool is a really good starting point, but let's scale it to the reality of the math.
Okay.
Imagine you have 1 billion tiny waves in that pool, representing all the possible paths of a calculation. You have to program the wave generators, which in a quantum computer are the quantum gates.
Right.
You program them so precisely that 999 million of those waves crash into each other and flatten out completely.
Wow.
That is destructive interference hiding the wrong answers. You're engineering it so that exactly one giant wave, the correct answer, gets amplified and splashes over the edge.
That is mind-bending.
It is. You are steering the probability so that when you finally measure the system, the overwhelming likelihood is that you'll read the one outcome you actually want.
It is essentially a highly orchestrated mathematical symphony.
That's a great way to put it.
And I know it relies on another strange property to link those waves together, which is entanglement.
Entanglement is totally crucial. It is when qubits share a joint state that cannot be described independently.
Like they're connected somehow.
Right. What happens to one instantly correlates with the measurement of the other, no matter the distance. This allows those probabilities to correlate in ways that act as a massive computational resource.
Got it.
But I want to correct another frequent misunderstanding right now. Entanglement does not transport people or matter or anything physical.
So the sci-fi dream of teleporting me through a wall is dead.
Completely dead. Furthermore, quantum teleportation does not enable faster-than-light communication.
Wait, it doesn't. I thought that was the whole point of spooky action at a distance.
No. While the measurement outcomes are correlated, the results you actually see locally appear entirely random. To make sense of them, you still have to call your friend on a normal light-speed classical communication channel, like a telephone or the internet, to compare notes and extract the useful information.
Okay, so the physics is beautiful, but eventually you have to build this symphony out of metal and wires. We are talking about translating these delicate probabilities into physical hardware. And there are a few different ways engineers are trying to do this right.
Several, yes. The leading candidates right now are superconducting circuits.
Okay, what are those?
They are microscopic loops of metal, chilled to near absolute zero, where electrical resistance basically vanishes, and they act as artificial atoms.
Okay.
Then you have trapped ions, where individual charged atoms are suspended in a vacuum by electromagnetic fields and manipulated by highly tuned lasers.
Sounds expensive.
Very. There are also neutral atoms moved by optical tweezers, and even systems using photons, which are just particles of light.
Okay, if the math is so powerful and we have these cool lasers and superconductors, why don't we just slap 1 million qubits on a board tomorrow and start solving the universe?
Because of the biggest enemy in quantum mechanics, which is noise.
Noise.
Yes, these quantum states are incredibly fragile. This introduces the concept of decoherence.
Let's break decoherence down. What is actually physically happening to destroy the qubit?
It's unwanted interaction with the outside world. Heat, for instance, is just atomic jiggling.
Right.
If a stray particle of heat bumps into a qubit, it essentially forces the qubit to interact with its environment. The universe basically measures the qubit prematurely.
Oh, so it forces it to pick a 0 or 1 before you're ready.
Exactly. The delicate wave function collapses before your calculation is finished.
Yep.
A thermal fluctuation, a material defect in the metal crosstalk between neighboring qubits, or even a stray cosmic ray from space can cause decoherence.
Just a random ray from space. That's wild. So that's why we are stuck in the current era of hardware, which I've seen called the NISQ era.
Yes, NISQ. Noisy intermediate scale quantum. It describes our current engineering reality. We have processors with dozens or even hundreds of physical qubits, but they are noisy.
So they mess up a lot.
Right, we can only run very shallow sequences of operations before errors overwhelm the calculation and the data just turns to garbage.
Wait, so if a massive tech company puts out a press release next week claiming we just built a 2000 qubit processor, I shouldn't be impressed.
You should view it with extreme skepticism.
Really?
Yes, because more physical qubits do not automatically create a more useful computer. If those physical qubits are noisy, adding more of them might just mean you generate errors even faster. Present machines are simply not broadly fault-tolerant.
This brings us to a huge distinction, the physical qubit versus the logical qubit. But I am genuinely confused by how you fix a quantum error.
It's tricky.
Yeah, because if you just said that looking at a qubit destroys its data, how on earth do you know if it's broken? That sounds like trying to fix a car engine while blindfolded.
It is exactly like that, and the solution is one of the most brilliant workarounds in modern physics.
Tell me.
Because of a rule called the no-cloning theorem, you cannot just make backup copies of a quantum state like you copy a file on a classical hard drive.
Oh, okay.
Instead, you use a quantum error-correcting code. You take the information of one logical qubit, which is the protected, stable unit of information you actually want to compute with, and you spread it out across many, many physical qubits.
So the physical qubits act like a protective shell.
Think of it like a grid. Instead of looking directly at the delicate data, you perform syndrome measurements.
Syndrome measurements.
Yeah, you measure the correlations between the neighboring physical qubits in the grid. If an error occurs, these boundary measurements change in predictable ways. So you extract information about the error without ever looking at the protected data itself.
Wow, okay. But how many physical qubits does it take to form this protective grid for just one logical qubit?
Well, depending on the raw error rates of the hardware, the overhead is staggering. You might need hundreds or even thousands of physical qubits just to sustain one single stable logical qubit.
Here's where it gets really interesting, though. That gives crucial context to the August 2026 evidence update.
Yes, it does.
I want to look at Google's milestones. Back in 2024, they published a paper in Nature about their Willow chip demonstrating below-threshold surface code memories. Please translate that into English for us.
I can do that. A surface code is that protective grid of physical qubits we just talked about.
Right.
For a long time, the hardware was so noisy that adding more physical qubits to the grid just introduced more errors than it fixed.
It made it worse.
Exactly.
Yeah.
But the Google 2024 milestone proved that they finally crossed the threshold. As they made the protective grid larger, the logical error rate actually went down.
They proved the blindfolded car repair actually works.
They did.
And in 2026, they followed it up with dynamic code experiments. But I'm guessing there's a catch here.
The catch is vital. These are phenomenal breakthroughs in creating a protected quantum memory. They are proving they can keep a qubit alive. But that is entirely different from building a full, fault-tolerant quantum computer executing a deep catalog of complex algorithmic gates.
I see.
We're still a long way from stringing thousands of these logical qubits together to actually run something useful.
Okay, let's play devil's advocate. Let's assume the engineers pull off a miracle and we get a machine with millions of stable logical qubits. What do we actually run on it? Can it run my video games faster? Can it instantly solve any math problem?
No, not at all. Quantum computers are not faster for every problem. This relates to computational complexity. There is a very common belief that quantum computers will effortlessly solve all mathematically hard problems like all NP-complete tasks.
NP-complete. Give me a practical example of what that means so I can picture the limitation.
The classic example is the traveling salesperson problem. If you need to visit 50 cities, what is the absolute shortest possible route? It sounds simple, but the number of possible routes grows so explosively that a classical computer would take billions of years to check them all.
Right.
It is widely believed by computer scientists that quantum computers do not offer a magical shortcut to solve these combinatorial explosions efficiently. They aren't a panacea for all hard math.
So what specific math are they good at? We always hear about Peter Shor's algorithm and Lovegrover's algorithm.
Right, so Shor's algorithm is famous because it offers an exponential speedup over classical methods for finding the prime factors of massive numbers.
Right.
And Grover's algorithm offers a quadratic speedup for searching unstructured data. It turns a search that would take 1,000,000 steps into one that takes 1,000 steps. That's significant, but not exponential.
Let's stick with Shor's for a second. Why is factoring numbers so incredibly difficult for a classical computer?
Because multiplication is a one-way mathematical function, basically.
Yeah.
It is very easy for a classical computer to multiply two massive prime numbers together to get an even larger number.
Sure.
But if I only give you the final massive number and ask you to reverse engineer which two primes created it, classical computers essentially have to resort to glorified trial and error.
That would take forever.
Right. But Shor's algorithm changes the game. It uses that quantum interference we discussed to find the underlying periodic structure of the sequence, revealing the factors almost instantly.
That brings up a terminology nightmare, though. When someone claims their machine used an algorithm to achieve advantage, what does that actually mean? You hear quantum supremacy, commercial advantage, practical advantage.
We must separate these rigidly because the hype blurs them intentionally. Quantum supremacy or benchmark advantage simply means a quantum computer performed a highly specific, often mathematically contrived task faster than a classical machine could.
Give me an example of that.
For example, simulating its own random circuit noise. It proves the machine is doing something uniquely quantum.
Yeah, but it doesn't mean it's doing something useful.
Exactly the point. This is a massive misconception. Benchmark advantage does not automatically establish commercial usefulness.
Yeah.
Just because a machine can sample random noise faster doesn't mean it can simulate a new drug.
Right.
Practical quantum advantage means solving a real-world problem better than a classical machine. And the holy grail, repeatable commercial value, means doing it reliably cost-effectively and actually integrating it into a business workflow.
With that brutal definition in mind, let's put Michio Kaku's visions to the test. His book presents a map of incredible possibilities. We're talking about curing currently incurable diseases, designing materials for infinite fusion energy, solving climate change, ending world hunger with revolutionary fertilizers. It sounds amazing.
It is an inspiring vision, but I have to state clearly for the record, quantum computers have not already solved climate change, fusion, drug discovery, world hunger, or incurable disease.
How do we evaluate these claims without just being cynical about everything?
We apply a 5-question audit to every proposed application.
Okay, what are the questions?
1. What is the exact computational bottleneck? 2. Which specific quantum algorithm addresses it? 3. What are the realistic hardware requirements? 4. How will the answer be verified? And 5. How does it compare to the best evolving classical baseline?
Okay, let's audit chemistry. Simulating nature seems to be the strongest native use case for these machines.
It is. Classical computers struggle to simulate molecules because the interacting states of electrons grow exponentially.
Okay.
If you add just a few more atoms to a molecule, the classical computing power required to track the electrons doubles, then quadruples, then spirals out of control. Since quantum computers operate using the same quantum rules as the electrons, they are naturally suited to model them.
Oh, that makes sense.
So simulating the catalytic reaction for nitrogen fixation, which is how we make fertilizer, is a mathematically proven fit.
But I'm starting to see the gap here. Calculating a better molecular energy estimate in a quantum processor doesn't automatically mean we've revolutionized global agriculture.
Precisely. To solve world hunger, you don't just need a theoretical molecule. You need arable land, new farming systems, industrial-scale manufacturing, and global supply chains.
Right, it's real-world stuff.
Exactly. The same goes for drug discovery. A quantum computer might flawlessly model how a protein folds or how a new compound binds to a target. But a calculation is not an FDA-approved medicine.
You still have human trials?
You still have to deal with human biology, toxicity, years of clinical trials and manufacturing. The quantum calculation is merely one link in a very long, very physical chain.
Okay, so if simulating quantum physics makes intuitive sense, what about something inherently classical? Silicon Valley is desperately trying to smash quantum computing and artificial intelligence together. Is there an actual fit there, or is that just buzzword bingo?
Well, there's a massive physics roadblock there. If you want to use a quantum computer to train an AI model on billions of classical text documents, you hit a brutal bottleneck called data loading.
Meaning just getting the information into the machine?
Yes. Encoding terabytes of classical data into delicate quantum states takes time and immense resources. The overhead required just to load the classical data can completely erase the theoretical speed-up the quantum algorithm was supposed to provide in the first place.
Wow, so it slows it down.
Right. Unless the data is inherently quantum to begin with, like data coming directly from a particle accelerator, the end-to-end advantage for classical AI is very difficult to establish.
Let's pivot to the one application that honestly terrifies people: cybersecurity.
Right.
If Shor's algorithm can easily find the prime factors of massive numbers, and almost all of our modern internet encryption, like RSA, is based on the difficulty of factoring those exact numbers. So what does this all mean for our bank accounts? Are we doomed?
First, let's stop the immediate panic. Quantum computers have not already broken modern encryption. There is no cryptanalytically relevant quantum computer in existence today.
Okay, phew.
Yeah, the machines we have are far too small and way too noisy to run Shor's algorithm on an encryption key.
But the threat is real for the future, and I've heard intelligence agencies are worried about something called harvest, now decrypt later.
That is the real danger, yes. Adversaries can soup up encrypted data today, state secrets, intellectual property banking protocols, and just store it in a massive data center.
And wait for the tech to catch up.
Exactly. 10 or 20 years from now, when a large-scale fault-tolerant quantum computer does exist, they can run Shor's algorithm and decrypt it retroactively. That creates a present-day risk for any information that needs to stay secret for decades.
But how do you defend against a machine that hasn't even been fully built yet? Do we need our own quantum computers to fight back?
No, and this is a critical point. You defend against it using classical math. Through proactive risk management, the security industry has been developing post-quantum cryptography.
Okay.
In August 2024, NIST, the National Institute of Standards and Technology, approved the first finalized post-quantum encryption standards.
What are those?
These are entirely new mathematical algorithms that run on your normal classical hardware, like your phone or laptop. They rely on completely different math problems, like lattice-based cryptography, that Shor's algorithm is fundamentally bad at solving.
Oh, that's clever.
Yeah, we are updating the classical locks before the quantum lockpick is finished.
That is a huge relief, honestly.
Right.
All right, taking all of this evidence together, from the sheer fragility of the qubits and the staggering overhead of error correction to the strict definitions of advantage and the reality checks on these applications, what will the actual quantum revolution look like? Because it definitely isn't a shiny quantum laptop I can buy at the store.
No, you will never have a quantum processor in your smartwatch.
Darn.
The likely mature architecture is a hybrid workflow. Quantum processors will be powerful, highly specialized accelerators sitting inside massive, supercooled data centers.
Okay.
They will work directly alongside classical high-performance computing systems.
So similar to how my computer offloads graphics processing to a GPU, a data center, will offload a very specific chemical simulation to a QPU, a quantum processing unit.
That is the most credible forecast, yes. We will always need classical computers for compiling the quantum circuits, running the complex cryogenic cooling systems, processing those massive error correction syndrome measurements in real time, and handling the inputs and outputs.
And what about the timeline? Because if you look at industry roadmaps like IBM's January 2026 targets, they're aiming for massive scale and fault tolerance by the end of this decade.
Corporate roadmaps are incredibly useful for organizing engineering efforts and securing funding, but they are expressions of intent. They are not completed achievables.
Right, they're goals.
They are conditional scenarios based on assumptions about scaling physical qubits and drastically improving error rates. As IBM and others openly acknowledge in their technical literature, these are aspirations. They are targets, not guarantees.
So we're not looking at a magic wand that instantly ends world hunger and cures every disease. We're looking at a brilliant, deeply complex new tool that requires a symphony of classical engineering just to keep it stable.
Very well said.
But for me, the most fascinating takeaway isn't the hardware. The ultimate bottleneck might just be us. The true test of quantum computing will be whether human beings can creatively formulate the right structured questions, the exact algorithms that make this machine's unique physics actually useful. If we can't figure out how to ask the right questions, the most powerful computer in the universe is just an incredibly expensive refrigerator.
I think that is the perfect perspective. It's a testament to human ingenuity that we can even build these devices.
Yeah.
But the true revolution won't be measured by the number of qubits. It will be measured by the validated practical knowledge they eventually help us create.
This has been an independent COSMORA HQ book overview presented in audio podcast format. It is not an audiobook. Complete narration, adaptation, abridgment, reconstruction, authorized edition, or substitute for Michio Kaku's original work.
Yeah.
Which possible use of quantum computing would you most like to explore further? Medicine, cybersecurity, clean energy, artificial intelligence, materials, or fundamental physics?
I'd love to hear your thoughts on that.
If you enjoyed this COSMORA HQ audio podcast, please like this episode, share your answer in the comments, and tell us what book, scientist, technology, or scientific question you want to listen to next. Subscribe to COSMORA HQ for more independent explorations of physics, space, science, and transformative ideas.